Hello, this video abstract is for the work Generating Distributed Entanglement from Electron Currents, accepted by NewJournalofPhysics. The work is a collaboration between these following authors. If a pair of particles has the property of quantum entanglement, then the particles are correlated in a way that would be impossible using classical physics. Entanglement can be regarded as an essential ingredient for any quantum information processing tasks, which outperform their classical counterparts. For the past decade, numerous efforts have been put into the generation of entanglement in various quantum computing architectures, and there have been many experimental demonstrations. It is, however, particularly difficult to create entangled states in solid-state systems, since one has to exercise precise and unprecedented control on the nanoscale, while tackling the difficult problem of decoherence, the loss of phase information. On the other hand, owing to the current manufacturing expertise, it would be very desirable to have simple entanglement generation schemes in place for solid-state systems, since they can conveniently interface with current semiconductor-based computer technology. Typically, in a solid-state system, in order for two qubits, for example, two electron spins, to become entangled, they must interact for a period of time. In many schemes, this requires active intervention in the experiments to turn on and off the interactions. In a scheme we shall describe, no such control is necessary. Two streams of electrons emitted from a source, and two static electrons downstream become entangled without any external intervention. Interestingly, a passive source of maximally entangled electron spin pairs of the kind that we would require have been demonstrated by two recent experiments. In our scheme, we position a static spin close to each current carrying leads with arbitrary distance downstream the source. Possibilities for the realization of the static spins include single electrons confined in quantum dots in gated semiconducting quantum wires, and those isolated by the minima of surface acoustic waves. Individual florins in the carbon nanotube p-pods or the nanobud structure could also be feasible. When a flying spin encounters a corresponding static one, effective spin-spin exchange interactions take place. We found that with each passing pair of flying spin singlets, the static spins become more increasingly entangled and eventually saturating with a remarkably high fidelity entanglement. The actual time it takes for the convergence towards the attractor state depends on the coupling strengths. We also found the entanglement generated is robust to decoherence for large enough currents. Notably, our scheme produces a static pair of highly entangled electron spins that can have a much higher degree of separation than more conventional protocols for entanglement generation, for which the separation is limited by quantum tunneling or similar local interactions. We hope you enjoy the analysis in the paper. Thank you.